Okay, so welcome back to the second half of your fifth class or third time with me. Right, before the break, two periods ago, we talked about the deep connect between machine learning and AI, right? So machine learning really builds AI, and we are focusing on predictive AI, by which I mean it's a very broad category of AI where the objective is to get to some insight, something that is relevant to ground truth, something that's is not purely imaginative. Okay, whereas generative AI, by the very nature of the algorithm, is about being creative. Okay, and just like I've probably said many times, an AI that is talkative like a 5-year-old, gives really silly narrative about running into a dragon that breathe fire and something like that, and having a friend who's invisible, that's fine. Okay, so that's imaginative. It has nothing to do with ground truth. It has no insight into reality, but it is very much human-like. So that's not to say that generative AI, in the guise of large language model, doesn't contain truth. In fact, we will see when we talk about generative AI, when we talk about large language model, when we talk about generative pre-trained transformer, GPT, when we talk chat GPT, it will turn out that if you ask it a sensible question, it will actually give you a correct answer virtually, 90%, 95% of the time. Okay, so that's quite an accomplishment. But anyway, with predictive AI, really, it pays to be correct rather than it pays to be creative. But that's the line I want to get that. And so in your class, and to even a strongest extent, in my data analytics class, where I literally apply all kinds of techniques up to including AI inspired methodology to analyze data, then the ground truth or extracting real insight from empirical or real data is really job. Okay, in data analytics, you don't need a chatbot, you don't need to be human-like, you just need to give the right answer. Okay, in fact, yeah, my book just came out. It's not in the bookstore yet. Just kind of like arranging that right now. Well, my book is about data analytics, and we employ three toolkit. One is interactive visualization, which means, if you can visualize the data right, you get the insight right away, you can action on it. And also it helps inform your model building. Okay, so it's used as an end tool, and it's also used in the process of building quantitative models. Okay, second group is probabilistic modeling, so that's more like traditional distribution. And the third part is machine learning, and all this is done on Mathematica, again, because it's very high level, very powerful language. The point is that with machine learning, the focus would be on supervised and unsupervised learning. This book, as in my lecture, entirely skip reinforcement learning because it probably has more, well, it doesn't probably, it definitely has a lot more relevant to robotics, control, and so forth than it does with data analytics. Okay, although reinforcement learning does feature fairly prominently within the context of large language model as well. If you think about it, it's like, well, a large language model is generative, so it can be creative, it can be truthful, it can be false, and the quality of the response, in a way, is something that has no immediate right or wrong sense, right? So maybe some kind of feedback from a real human being over time might be useful, and that kind of like long arc evaluation improvement resemble reinforcement learning. So that's why there will be this thing called human feedback reinforcement learning that pops up in the context of large language model. Yeah, but back to today. So today I'm going to show you a snippet from chapter 1, 2, 3, 4, 5 or 6, which is about the machine learning aspect. Okay, so this would be something that I think this is chapter 5, right? Chapter 5 is about unsupervised learning, but today is about supervised learning. Now, I just show you this two picture. It's an excerpt from the book. We'll go through the interactive calculation, but you can see from the left picture, right? What I want to draw your attention to is the left picture is kind of like a regression problem. Okay, think of it as a regression problem. Y is a function of x. Okay, in this case, it's not a linear, so linear would be underfit, right? If you try to fit all the point, it will be overfit. So the optimal fit by design is some kind of a curve fit, right? Kind of curve fit. Now, the bottom right, you can see this thing called RMSE surface. Now, the way I make this, even though it is a curved line, so it has a second has a square term of x. I only have two parameters. Okay, I only have two parameters in this problem, and so you can think of it as this thing here, right here, that valley. That's the hill that we want to go down. Okay, and if you notice the top right, there's like a squarish thing. Let me show you what it is. Okay. This squarish thing, okay, I don't want to zoom, I just want to highlight quickly, right? So this is one parameter, this is another parameter. This is the location of the optimal value. Okay, so basically beta 0 and beta 1 that I should get to. Now, the regression equation is a one-shot thing, right? It's a one-shot thing, I told you already. So you should get the right solution right away. From 0, get to that point. But if you do this incrementally, which is what you would have to do for a more complicated, neural network, convolutional neural network, this kind of AI engine, is to go step by step. And before the break, I already show you. So let's say I start here, I would have to incrementally move until you get there. The right picture, I want to show you quickly, which is to say this, okay? Now, think of that problem where I was saying that on this x-axis is the weight, right? And the higher you are, the likely you are to be men, let's say, okay? So imagine that instead of have the weight, I also have the height, okay? Then maybe the higher the weight and also the taller you are, the more likely to be men, okay? So imagine this room, right? Imagine this room is data plot. So from left to front right, this is the weight. Okay, from front to back is the height. So I want you to stand where your weight and your height combination is. Okay, imagine, right? And chances are that far right corner right there, which is very heavy and very tall, is going to be mostly men, let's say. Over here, it's going to be mostly women, mostly girls, right? That makes sense because shorter and lighter. Okay. Now, again, that step function, in this case, now become a step surface, right? So I have a step surface that has a lot of 0 over here, and at some point, it becomes a lot of 1, right? So think of that, right? Except you can think of this function. Well, if you look at it sideways, is this function linear? No, it's a step function, right? It goes from 0 and then jump to 1. So it's not a linear function, right? It's not a linear function. However, if I look from bird's eye view and I look at the partition it creates between a lot of 0 and a lot of 1, that partition will follow a straight line. Can you guys see that? Okay, watch my hand. Watch my hand. Okay, again, light, heavy, short, tall. And most women are over here and most men are over there. And let's say, okay, for the purpose of this argument, this 45-degree line is a very good line for separating girls from boys. Okay? What is my predictive model supposed to look like? Well, it's supposed to give you a lot of 0 over here. And then just about where my arm is pointing, okay, this 45-degree line, it goes up to 1. So that line is nonlinear. Okay? So look at my arm. That line is nonlinear. But if I look from the bird's eye view, that jump, that transition from most 0 to mostly 1, that follows a straight line, right? So in that case, what we would call linearly separable data set. Okay? So this category between boys and girls, in this case, right, can be separated by just one step function. Okay? However, that one step function is like bottom left here, one step function. Okay? Imagine now, if instead of having one step function, I superimpose another step function that is oriented at some angle. Okay? And in this example, I happen to just make 3 of them. 3 of them. You can see that the end result on top there is a separation which is not linear when you look from the bird's eye view, right? Okay, can you see this? Bottom left, right? The bottom left. Can you see this? Okay, the bottom left. Okay. When you look from the side, it's not a linear function, it's a step function. But when you look from the bird's eye view, the separation between 0 and 1 is a straight line, right? That's what we mean by linearly separable. Okay? So if it happens to be that the girls are over here and the boys are over here and the straight 45-degree line that, you know, as my arm, look at my arm, this 45-degree line happens to be a line that nicely separates boys and girls, then I would say that boys and girls are linearly separable with respect to the weight and the height. Okay? But in life, this linearly separable is a very rare thing. Okay? It's too naive. It's too simplistic. So how do we correct for that? Well, we have to go to non-linearly separable capability. So let's say, for example, let's say for some reason, okay, these are the boys and this here is girls. Okay, look at my hand. From here is girl. So the function that I want to separate between 0 and 1, if you look on top from bird's eye view, is it going to be like this? No, it's going to be like this, right? Like some fancy step function in a hotel, you know, those hotel that doesn't have a straight stair, but the curved stair, right? So this is non-linear separable. The point is this. Just as linear regression has 2 coefficients, if I want quadratic, I add another coefficient. I want third order, I add another coefficient. The way to add non-linear separation is by adding additional linear separation. So basically, to create this curve, what I want to do is one straight line here, maybe one straight line here, and one straight line there, and sort of like add them together, right? Connect them together. Does that make sense? This is the compositional nature of this function. This is exactly how a neural network does. Okay? A neural network that detects cats and dogs and your voice and whatever, okay? Fundamentally does this composition of incremental separation, okay? So you can imagine that, you know, instead of being boys and girls and weight, it now could be boy versus girl versus adult versus old age versus cat versus dog, okay? Versus shark versus elephant, okay? These are all separable, but not with a line, but with really fancy curve. And fancy curves are constructed incrementally by doing this. Now, in reality, it's even more than this. Not just three, a whole bunch more. And not just once, layers of them. Okay. This individual step function, okay, is similar. And this is where, okay, you see this? Okay, let me quickly detour to screen. Okay. So now, the function, right? Can you see this? I want to create something like this. Does that make sense? Yeah. So this is x1, x2, and this is y. So there's a step function. Okay. Now watch this. This line, this red line is straight, right? So how do I create that? Well, it's some combination of W1 x1 plus W2 x2. And when I did this, it points this direction. Okay, look at me, look at the board. Okay, look at the board. So this is x2, this is x1. Okay, on top, let me do this. x1, x2. Okay, W1 x1 plus W2 x2 is going to be some kind of direction vector. So let's say it's pointing this way. Pointing this way. Okay. The idea is that based on certain threshold, if the value is beyond this threshold, I give it a 1. If it's below this threshold, I give it a 0. Okay. Okay. So this is going to be a direction of this W1 x1 plus W2 x2. If it's below this certain level, I'm going to give it 0. If it's above certain level, it's going to give it a 1. Around here, maybe I give it a 0.5. So you can imagine that there is a 1, 0 function over here. Okay. Does that make sense? This is only 1. Okay. So now, imagine that I don't have just 2 dimensions. I have x1, x2, x15 dimension. So I can't do just separation like this anymore. It's 15-dimensional space. Okay. So now I'm going to do the same thing. I'm going to call it W1, W2, W15, right? This, by the way, is called dot product. So this, again, is going to be an arrow. It's an arrow in 15-dimensional space. And if it's strong enough, I'm going to give it value of 1. If it's not strong enough, I'm going to give it value of 0. So this function, this value here, I'm going to draw it like this. Okay. And then that's my output. Okay. Right. Now, Google, well, I don't have to do it now. Google neuron, human brain. Human brain, the neuron looks exactly like this. This is your cell. This is input. This is called dendrite. This is called axon. This dendrite is an input. It has chemical potential. So basically biological multiplication. It has certain threshold. If the signal is strong enough, it sends electrical signal down. So sending electrical signal is equal to 1. No electrical signal is equal to 0, right? So basically, each one neuron in your brain can do linear separation. The reason you have complex thought is because you have billions of neurons. And we saw the picture that with just 3 neurons, I can make a little bowl shape. Imagine if you have billions of neurons, how complicated a function that you can make it, right? So that's why when scientists, when they did this, they have this, okay? Okay, this is one neuron, this is another neuron, this is another neuron. Historically, neurons are based on perception neurons, so they call it perceptron. And then they stack this into this, and they keep doing this. This thing is organized like a layer, because actually, if you dissect your brain, the brain is actually organized in layers. Okay, not always. No. So more than one layer, multi-layer perceptron. Okay, remember that word because that'll be on the exam. Multi-layer perceptron is a computational analog of your brain. The reason it can do amazing thing is because by doing this simple 0, 1, incrementally, you can create any function. Okay, now you can write anything. Don't have to look at my hand. Okay, so now let's go to example, like I said, okay. Now this is called supervised machine learning, okay. So I'm just gonna skip some of this. So basically, I just want to show you, well, this is basically what we saw earlier, right? So what's a linear regression problem? Well, linear regression would be straight line. This is non-linear, but what's a regression problem? If the best solution is here, you jump in one go, okay? But if it's a gradient descent, let's say gradient descent, okay? It's like this. And go one step at a time, one step, until you stop here. Oops, sorry, I overshot. Okay, there, right? Again, so this is a perfect fit. Would you agree? Right? Would a straight line be better? No, it will be underfit. Would a squiggly line be better? No, it would overfit. Right? Again, I want you to understand that with linear regression, if you have 2 parameters, there's no point. Okay, you can't overfit anyway. Imagine that what I just told you, right? With just 3 neurons, you can make it complicated. And human beings have billions of neurons. A deep learning has thousands and sometimes a million neurons, so it can easily overfit. That's why in supervised machine learning, overfitting is important. You don't want to minimize error all the way. Okay? It's kind of funny. It's kind of opposite problem with generative AI. With generative AI, it's being creative. So you have to bring it back to reality. Okay? With predictive AI, it's trying to fit reality too much because every single data point is a reality. So if you don't stop it from fitting reality, it can't imagine what generalization would take. Does that make sense? Does that make sense? So the present data is reality, but to imagine what the future world is like, you have to be able to generalize. And to generalize, you cannot fit all the reality here. Okay, so it's kind of the opposite challenge, right? So again, with predictive AI, you don't want to learn all the things. Okay, so now, so this is a very good exercise to show you. So by the way, if you have that one neuron in statistics, it's called logistic regression. So if you have a friend who does logistic regression, you say, yeah, all it does is solve linearly separable problem. Now, in things like population statistics, maybe it works. Because if you think about it, things that are, averaging out on the large scale. For example, if I'm going to predict probability of early death, right? Chances are the more you smoke, the more you drink, the worse you get. Okay, so maybe you don't need something that sophisticated, right? So I just line up from non-drinking to drink a lot, non-smoking to smoke a lot, and I measure the age. So maybe it would be very simple, right? A straight line, okay? The more you drink, the more you smoke, the earlier you die. End of story. So maybe, yeah, in some case, logistic regression work, but something more sophisticated, it wouldn't. Now, here's what I want to show you. Okay, so we saw this already, right? So this is a thing. Okay, now, where are we? Okay, here we go, 212. So artificial neural network is a general term. Okay, I gave you one term, multi-layer perceptron. Imagine that multi-layer perceptron, but different architecture. Maybe the function is different, maybe it's connected differently. So it doesn't have to look like layers of perceptron. The whole thing, the whole area of research is called artificial neural network. Artificial because it's mathematical, right? It's not biological neuron. So if you think about it, the brain is a biological neural network. Okay, everything else is artificial. So artificial neural network. Okay, there it is. Okay, so right, and basically, I can move things around, blah blah blah. Now, so far has been insight. Let's get practical. Let's imagine that you are not really a data scientist, right? You're just working on sustainability track. You're working on health and well-being, and you have a data set, and you want to predict Y from X, right? Y from X. And you know that it's not going to require, say, large language models, billions of parameters. You want to do some prediction problem of your own. Now, imagine this is something that you want to do literally on your desktop. Okay? Could you do it? Definitely. Right? After all, regression is a form of prediction problem, right? So you can do that in your computer, you know that. So let's do that. Now, the way, the steps here, okay, I highlight this as a procedure. Now, individual step can take weeks and months in the real problem, but sometime in your data set, it could be very simple, okay? It could be something you can do in 5 minutes. This is what I mean by doing things in 5 minutes. First of all, because you know you can overfit. You don't take the whole data and feed it to your model. So first thing you do is you partition your data set. So this is basically step one. So in my case, this is not the actual data. This is a representation. Okay, X1 and X2 go to Y1. X1 and X2 go to Y1. So these are all the 1, 2, 3, 4, 5, 6. So these are all my training set. And this is my test set. Okay. Now, in theory, there's more, fancy validation. So I'm not going to burden you with that because this is not a machine learning class. But anyway, I want to show you how simple life can be. So imagine you're working on sustainability problem or health and well-being, and you have a prediction problem. Okay. So for this purpose, I'm going to say you have two problems. One is prediction. So numerical prediction. Okay. Y given X. Could be many X's. Okay. The other one is classification. So Y would be categorical. 1 for a cat, 2 for a dog, 3 for a turtle, 4 for a shark, or something like that. Okay. So you have two problems, classification and prediction problem. Okay, you have two problems. Let's see how easy life can be. Now, because your data can be different, I'm just going to come up with a toy data. And in Mathematica, okay, you have a whole bunch of example data you can play with. So once you can follow that, you can substitute your own data set. But so I'm in this class, in this book, I created two data sets. I take two data sets, okay? One data set is called Boston Homes. So this is predicting house price. So this will be relevant for this in marketing, okay? So you take in things like location, size of property, closeness, proximity to highway, to shopping market, and then you predict how much of a value of that house is, okay? So this would be called Boston Home example data. Okay, so this is curated data, so I don't have to clean it or anything. Here's a summary. A home value for 506 Boston suburb with potential influence factors such as crime rate, number of room, distance to employment center, etc., etc., etc. Okay, so the variable is all numerical. So all the inputs are numerical and the output is numerical. So literally, this is like a regression problem, right? Except more sophisticated. You can do, okay? So how many X we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, 13 factors. Now, this is how easy it is to build a model, okay? So look at the screen. Okay, first of all, I partition the data into training and test set. Normally, I would say take 90% for training and 10% for testing, right? In this case, I don't have to do the partition because it's already, you know, it's already separated. So this kind of, okay. But I can do my own. So this is my prediction data. I will call it predict data train and predict data test. Oops. Did I do? Okay. Why this? Oh, that's line. That has nothing to do with this. Okay. Right. Now, the other problem I have is classification. This classification is going to output Y, which is nominal. 1, 2, 3. And 1 is not worse than 2. 2 is not better than 1. Okay. In other words, what I'm predicting is 3 species of flowers. Okay, and you're not saying that 1 is a bad flower, 2 is a better flower. No, just 3 different flowers. In fact, there's a name to it. Where's the name? Yeah, this one is called Setosa. The other one is called Vesicolor, and the other one is called Virginia. This is just variety of flower. Okay, so the data set here. Okay, the data set here is, I'm gonna call it train and test, but because it's a classification, I'm gonna call classify data train, classify data test. Okay, and these are the numbers. Okay, so 2 data set, 1 is classification problem, 1 is prediction problem. Each of them I split into train and test. Right? Okay. Now, this is how easy it would be for you to build a model. There. Okay. Call this built-in function called predict. I'm building a predictor. I call a function called predict. This prediction function is using the trained data. And once I train it, I name it as predictor. Now, just for curiosity, now in Mathematica, it's a very declarative thing. You say, I would like to have a predictor. That's all you need to do. But let's say I'm a little bit more picky. I want to specify the type of predictor. And this is more closely related to a functional programming. Like in Python, you have to specify what method you use. In Mathematica, you can say any method will do. But alternatively, I can specify the method. So I show 2 examples. So one example is called predictor. Just give me any prediction, any predicting machine. The other one is called predictor NN. So I want to use neural network. Okay. And this is, okay, so let's do this from scratch. Okay, you guys ready? So I'm actually training 2 models for this predictor. Shift enter. Okay, it's 1 second, 2 seconds, done. So 2 seconds done for the first one, 3 seconds, 5, 6, 7, 8, 9, 5 seconds, 6 seconds, 7. It's actually, this is the error function. It's based on standard deviation. I think this one maybe take a bit longer. Yep. So the error is going down. The error is going down. The point is, you know, with professional or you know, more free software like the language like Python, you may need like 10 lines to do this, okay? Whereas here it's a more decorative. You just say one line, build me a predictor, okay? Build me a predictor, and there it is, 39 seconds. So let's say, okay? So it's gonna give you a predictor. Likewise, okay, 42 seconds, okay, fine. Likewise, for the classifier, I do two model. One is give me any classifier. I'm gonna call a function called classify. And the other one is classifier using decision tree. Okay, so I'm gonna say, okay, let's start doing that. Okay. Oh, this is even quicker. So this is half a 0.9 of a second is done. So, by the way, you can go back and say, if I didn't specify what predictor it chose and ask Mathematica to come up with one, it's gonna try to use something simple like random forest. So there it is, that's a random forest. Okay, but if I specify that it's a neural network, then it will be a neural network. Likewise, here, if I require it to be a decision tree, it's going to be decision tree. If I don't require it to be decision tree, hey, logistic regression works. Okay, so this problem is so simple, logistic regression works as well. Now, so that's it, that's training. Testing, likewise, you know, if you program it with you might need a few lines. So here, I'm just going to make one line. That function is called predictor measurement. So basically, measure the error. Instead of testing just accuracy, it's going to test all kinds of statistics. Not next week. You would have taken some probability statistics class, right? And then you will be familiar with numbers like R-square, root mean square error. So this thing is like that. Okay, so shift enter, and there it is. So it gives you all kinds of statistics like R square, mean entropy score, mean cross entropy, doesn't mean anything to you, never mind. And this is it, this is, okay. Now, you will see that there are two. The left-hand side is the accuracy with respect of the data that it's seen. So that's the in-same sample. And the right-hand side is the testing, okay? So this would be the 90%, that would be the 10%, let's say, okay? I'm not sure what the proportion is, maybe 70-30. Okay, you can see that it's got similar kind of error. So this case, by testing, you can see that, yeah, it's not overfitting, right? If it's overfitting, what's happening? If it's overfitting, this thing would have no error. Okay, the predicted value and the actual value would line neatly on the 45-degree line, 1 to 1, 1 to 1, 1 to 1, 1 to 1. And the out of sample or testing data would have terrible error. In this case, it's roughly the same. Yeah. So it's pretty good model and it's not overfitting. So you're happy. Well, you should be because this is an easy data set. Okay, house price prediction is very easy to do. Okay. Now let's try something else. Now, this is about predicting numerical value, right? The other one is not predicting numerical value. It's classifying flower type 1, flower type 2, flower type 3, 3 types of flowers, right? So how do I report this? Well, it's going to look like this. Oops. Okay. Okay. Actual class, Setosa, there are 35 of them. And the model predicts 35 of them. Perfect for Setosa classification. So it actually makes 2 errors. There's one case where it's actually Virginica, but it's called versicolor. So 2 errors. This is actually from the training. This is from the testing. The testing actually makes 1 error. But of course, the testing size is smaller. Okay. So this right away is how you would do it. So imagine that you're working on a very simple problem in your, sustainability, health science, and stuff. You want to predict whether or not you have this beauty product, and you have certain demographic characteristics and so forth, and certain kind of products, and you say, am I going to predict that this person's going to buy this, not buy, or buy a lot, let's say, okay? So instead of having setosa versus versicolor versus virginica, you could be predicting buy, not buy. Or you could be predicting not buy color red, buy color blue. Okay? If you can do that, then certainly for the client community that is going to be buying blue, you'll be stocking a lot of blue. Okay? For the client group that you predicted will be buying red, you stock red. Because if you stock blue, they want red, they're not going to buy. Okay? So any kind of marketing is like the easiest problem to do with predictive analytics, marketing. And I can imagine that marketing is going to be at the tail end of most of your project. At some point, you're going to involve marketing, right? So whether or not you're predicting a value, so that's predict, or classifying, it can be done in one line fairly accurately. Okay. Having said that, in real life, data is probably going to be more challenging. The first run is not going to get something this easy. This is like so nice. You can use it right away, right? So accurate. In real life data, chances are you need to do a lot of tweaking. Okay. One of the tweak would be, for example, specify the method. But just saying that you're using neural network or decision tree, that's not enough. Maybe you have to specify more. Okay. What kind of neural network? If it's multi-layer perceptron, how many layers of perceptron? Okay. If it's decision tree looks like a branch, right? And there's a depth to it. So maybe if you branch it 3 times, it's good. If you branch it 5 times, it overfits. If you branch it 2 times, it underfits. So maybe optimal number of branching is 3. So you have to play with this kind of like meta parameters, kind of like tweaking. Okay. So yeah, professional data scientists have to do more than that. But for your project, if you're not in applied digital intelligence track, right? You're in sustainability or health science, you want to do simple prediction application. You want to infer something about your data, about your client, about your market size. This is essentially how you would do it. Essentially how to do it. Okay. Right. So with that, I have one more. Okay. This is also ROC. This is kind of reporting performance as well. With that, I only have one more thing to cover today. Okay. Let me go back to the screen. Okay. Let me stop share here. Start share. Okay. This is how I run my thing. You guys know what a consultant is, right? Well, consultants are a bit like psychiatrists. You go to them with a problem and they're supposed to give you a solution. Okay. That's traditional way of thinking what consultant does. Go to them with a problem, they give you a solution. Okay. More modern consultant, you go to them with a set of pain point, and they help you define the problem. And they help you work out the solution. Okay. With data science, it's even more involved in that. As a data science consultant, clients come to me with their, say, issue, pain point, what they would like to do. They would like to increase customer engagement. They would like to do this and that, blah, blah, blah. I help them define problem. Okay. But I can't help them work through the solution because the solution will require data analytics. Okay. However, this is how data analysts used to work. This is how analysts use the word. I want to predict Y. I want to predict Y. I have X1, X2, X3 in my data. I perform regression analysis. End of story. Okay? End of story. Now it's not the same. Why? Number one, I can do more than that. So now, first of all, there could be more than X1, X2, X3. Or maybe the right way to view thing is to say X1 divided by X2. I don't know. Okay. But anyway, let's forget all that. Let's just say that at the end of the day, you have X. Okay. Now this is a mathematical notation for vector, meaning that it's not just one value, right? And you want to Y. Okay. So this is real Y. This is a model Y. And this is Y hat. The point is that this is how I do my data consultant work. Number one, I never try one method. I never try one method. Okay. And that has two consequences, which is a recommendation. Well, it's not a recommendation. It's almost a law for working with me. Never pick the simplest method because it's easiest. Never pick the simplest method. On the other hand, never pick the most complicated method. Okay. And I have problems like this as well. Some of my staff, want to show off that they are good with high technology. Use the advanced deep learning for something that doesn't require deep learning. Okay. So never use one method. I don't care if that method you choose because it's the simplest, wrong. You choose it because it's the most high tech, it's the sexiest method right now in 2024, wrong again. Use all that you can master. Why? Why? Because data science is an empirical. Data science is mostly empirical. What's empirical about it? You don't know which medicine works for which disease. Okay? Okay, let me say it this way. I shouldn't say that. Let me say it again. If you have a disease and these are the medicine, okay, that's science. Science tells you that if you have meningitis, you should take this. You have this, you take antibiotics, blah blah blah, right? The experimental or empirical part comes in that among the medicine that you can use for this disease, you don't know which one works for this client. Okay, so it's like antibiotic is a bad analogy because you should work from the simplest. Let's say you have one disease and you have 5 candidate drugs. The idea is you should apply them all. Now in medicine you can't, right? Because you have to try one at a time. But in data science, I try them all, from the simplest to the most complicated. Okay, that's number one. Okay, try them all. Number two, based on that, you select the one that perform best from your testing, not in sample, right? Because in sample, I can overfit, right? I can also underfit. The point is you have to select the best one. So the best one is empirically determined, the best. That's rule number 2. Rule number 3 in my house of analytics is that if the best one, again, in terms of accuracy or whatever, okay, if one is like a clear winner, obviously that's a clear winner, right? But if you have 2 winners, meaning that one has a 95.2 accuracy, the other one has 96.1 accuracy, okay? Essentially, they're both accurate. If they're similar in accuracy, I go for the simpler one, right? So when I try simple, complicated, 2-parameter model, 5,000 parameter model, I try them all. I would try them all. But if I try them all and the performance are similar, and one of them is a linear regression, and the other one is a deep convolutional neural network, which one would I use? I would use linear regression, right? Why? Well, for very first reason is it's very easy to explain. Okay, which brings me to the final topic of today. So again, okay, explanatory. Explainable AI. There's no such thing as explainable AI. You can't explain. You can't explain. You can try. You can try. Now, let's go back to linear regression. Do you need any explanation? You're almost done, right? Y is equal to 7 plus 3x. That means that regardless of whether or not you have x, you already get 1/7. 3. For every increase in x, you get 3. Right? That's your explanation. That's your explanation. You know exactly how the model produces y from x. So in terms of explanation, how x goes to y. Okay? With linear regression, it's obvious, right? The reason you get this y is because you have beta 0 plus beta 1 x1 plus beta 2 x2, add them all together, and you get y. So you know how it gets there. Can you do the same with, say, multi-layer perceptron? You can't. Okay, it's too complicated, basically. Okay, you can say in principle, but all the coefficient, you know, you don't have just 2 parameters, you have 5,000 parameters. So you can't do that. You can't explain that. So how about this? How about the role of x in determining y? Okay, look at the screen. Look at the screen. Those two look similar, right? The top line and the bottom line looks so similar, but not the same. The first one, you're trying to find out, you know, how do I use x? What formula I use to create y? The other one is, I don't know how x create y, but I would like to know, does x play a role? One of the simplest things you can ask is, if I have more x, would there be more y? All right? Now, you don't know what happened in between. So you don't know the formula. You don't know the calculation, right? But you're doing this. It's like what economists do when they go on news program. You know, all else being equal, if you have more demand, then you have price goes up, right? The mechanism is the complicated economy. So you need a PhD to understand the economy. But when you're watching television, you don't need that. You just need to say, okay, when this goes up, that goes up. I call it two-thumb economies. Okay? So it's very easy, right? That explanation is very superficial, but sometimes that's all you need. For example, if you have a complicated deep neural network model that predicts how your client is going to buy or not buy your product, okay? And all you have to be concerned with is whether or not I should throw in more money at advertising. Okay, let's say I have two options. I can throw more money at media advertising, or I can throw more money into research and development. Okay, and the answer is, well, the media is saturated now, so spend your money in research development. You may not know the internal AI that produced that prediction, but you know the conclusion. If I want to sell more, I need to do better research. Okay, if I need to do more, I do. So that's all you need. Okay, so I'm going to separate this. So this is something that's reasonable to ask. And I'm going to separate it into two questions. If and how. Now, the how is a little bit greedy. It's saying that if I have more of this, how would Y behave? Because most of the time it's not linear. If it's linear regression, yeah, obviously, right? Every time you increase x1, y increase by beta 1. Every time you increase x2, y increase by beta 2. That's how. Sometimes you can do that. But most of the time, what you can do is simply say, is x significant? So this is analogous to in your statistics class when you do the t-test, when you do the statistical significance test, right? When you read this regression equation, there's always numbers and there's all little stars. And if it's significant, it has 3 stars. If it's not significant, it has no star or something like that. So it's more like if. Okay. So the subject, the last thing that I need to cover today, yeah, we still have time, is like this. If and maybe how. Okay. Which brings me to Shapley. Mathematician, game theorist. Okay. If the 5 of you are sharing a cab to a restaurant, how should you split the cab fare? Divide by 5, right? Okay, fair enough. Now, what about from that restaurant, now you're going home, okay? You're going home, and let's say you live roughly the same area. So this is a restaurant. And this person lives here, this person lives here, this person lives here, here. So the cab has to drive here and there and back here and back here. Okay? Okay. Right. My question is, let's say you're not good friends, so you don't want even split. How would you share the cab? How? Well, a naive way would be something like the total distance is 10 kilometers, right? And how far is this distance? How far is that distance? How far is this distance, right? Would that make sense? Well, actually, it doesn't. It would only make sense if everybody lived on the same straight line. Maybe it might say, and even then, it may not make sense. Why would it not make sense? Because this one, right, takes all this distance, but it's not because this guy lives far. It's because this guy lives very far. So you have to go out of the way, right? So why should this person pay for this distance? Maybe this distance should be what he pays for, right? So how do you calculate all this? And this fall under the rubric of game theory, where you calculate this kind of group contribution. So we'll call it under attribution. Okay, how much of a total cab fare should be attributed to A, B, C, D, E, F? Well, one of the easiest way to say is to do the following. There are 8 of you. Okay, how much should each of you pay? Well, how about this? How about if you didn't come to dinner that day, how much would the total cab be? Okay, you came, your other friend didn't come. So basically, your contribution is evaluated in terms of your absence. And think about it, you do that all the time with sports, right? When this guy doesn't feel, this player is not fielded, does this team win or lose by how far, right? Something like that. Well, this kind of contribution estimation by evaluating or simulating your absence, okay, it traces this way back to Shapley. So what's that got to do with us? Well, instead of saying that there are 8 friends going to dinner and total cost is a cab fare, we say we have 8 variables that explain why. the contribution of X1 is what happened to that prediction problem if you didn't have X1 to begin with. Contribution of X2 would be, well, what would happen to the prediction of that Y if you didn't have X2? Okay. Now, again, the contribution is inferred indirectly. Your contribution is evaluated in terms of your absence. Okay. So if you want to know if your friends like you, basically check out your funeral or check out when you're not here. Okay. If you're not missed, you're not making a contribution. Okay. If one of you are not in class and the class discussion doesn't proceed or something like that, yeah, you're very valuable. Okay. But if you're here and you don't contribute anything or whatever, okay, then your contribution is 0 or negative even. Okay. It could be negative. This is called Shapley, and we have this thing called Shapley's explanation. Basically, if you don't know how the model creates a prediction Y from all the X, you can ask, what would the prediction look like if you take away some of the X's? Okay, and that's what this with Mathematica here, you just need one function. Okay, you already calculated this. One of the things that's in there is called Shap plot. Okay, Shap plot comes from SH for Shapley, A for additive, P for explanation. I think it was. I'm not quite sure. Anyway, so Shap also, or maybe Shap just means Shapley. Yeah. So it's Shapley or Shapley explanative, additive, whatever. Okay, and that's saying that the feature impact can be viewed. So remember the Boston problem, right? The house price. There are 13, I think, 13 input. So these are the contribution. The presence of F1 tend to push the variable to the right, and so this is obviously the more influence it have, the more of a spread in value of the Y. Okay, think of it that way. Okay, and there's even more, and you can look at this. So this is looking at all the data point, but you can actually have a version which look at individual prediction. In other words, for this Y, the reason you get house price estimation of $145,000 US is because you have positive factor from closeness to the street. You have this much contribution from a negative factor from being close to the crime area. So this thing drills down. Why is this important? Because, okay, just think of marketing. When you do a marketing regression, you're trying to find out which factor works, right? But you are not passive. You take control of those factors. So if you know which factor influences in which direction, you can, stick more money in that direction. Okay. So there's a difference between drawing regression to find the relation between X and Y and get an insight. This will be something like statisticians do. But if you actually have control, in other words, some of the X's is, from the environment. So you have no control. But maybe X7, X8, and X9 is something that you can influence. Well, then certainly you are not a passive observation anymore, right? Okay. So this is where, data analytics come in, and this is basically why data analytics pay for itself. It gives you insight that you can action. Okay. Sometimes it gives you insight you can't action. Sometimes, if all the variable are like in this case, it's just an insight. What influences house price? Okay, but I'm not in the market. I'm not real estate developer. I'm not choosing my property. I'm not, all I'm doing is just evaluating. I have nothing to do. But if X1 to X5 I can't control, but X6, 7, 8, 9 I can control, well, why not? Why not, right? And you can certainly do this kind of drill down. For the flower, there's only like 4 factor. I think it's some kind of length of the petal or something like that. Yeah, it doesn't matter. Okay, it's not that interesting. So this again, this is a toy problem, but illustrate the process. So you can see how easy predictive analytics is. There's almost no excuse for you not to apply predictive analytics in your problem. Number one, because predictive analytics can be so powerful, it can overfit. So be wise about your choice of data and your partitioning. Okay, so you prepare your data. You prepare your data in 2 senses. One is to make X point to Y. The other one is to say some of the data I keep aside for testing or whatever. Okay, so you prepare your data. Number 2, build the model. If the model is used for prediction, call the built-in function predict. That's it, you're done. If the problem is classification, you say classify and you're done. The thing knows how many classes there are. Okay. Number 3, test, right? Test the in sample, but most importantly, test the out sample alongside, and you can see that, oh yeah, it's overfitting or not overfitting. Okay, right? And finally, if you can choose a simple, if it comes up to be a linear regression, read the coefficient. If the best one turned out to be a deep convolutional neural network, you can't read the coefficient. What do? You use Shapley explanation. Okay, so the last step is kind of like an indirect step. You would need that if the best model by far is the most complicated. But once again, if the first and the second model are, close in performance, but one is a deep convolutional neural network, the other one is a linear regression, use a linear regression, guys. Okay, and that's basically it. So this is how you would apply. Again, the universe of AI for the next 5 years, I'm separating into two worlds, predictive and generative. Okay, predictive AI is still going to be a bulk of your application. Okay, and it's so easy. There's no excuse for you not to use it. Now, if you don't have a Wolfram Mathematica and you use Python, instead of 1 line, you may need 1 page of coding. But 1 page of coding is nothing. 1 page of coding is nothing, right? If the result is a better insight into business. Okay, so with that, the next times we meet, I'll do similar thing here, but instead of supervised learning, I would cover unsupervised learning. And hopefully this, I would not take the whole period for that. Then I would just take maybe half of it for that. And the other half is to go into, how generative AI work. But again, with generative AI, 175 billion parameter, there's no demo. Whereas this, you already saw, right? 10 seconds, half a second, 0.9 seconds. It's very quick, okay? So next week, we'll also have this live demo where you literally building the model in real time. Okay, Cap? So with that, I'll hand the microphone over to Marco, if you have any announcement.
Okay, a couple of things that I just wanted to fill you in with. First of all, if 2 weeks ago was the first time that you ever applied linear regression, please kind of revise the exercises that we went through together. Because, we have been saying for a couple of hours now that linear regression is easy, but it actually is compared to the other models that we are going to cover in 2 weeks. So that's the one thing that I wanted to tell you. The second one is things that we do over here in comparison with like data analytics that you do in real life. There is a big difference, other than, that it's like super professional that we can show you. And the big thing is that you need lots and lots of time to prepare both the data and the model. Over here, we have like stuff kind of readily prepared, and then we just show it, and then, it runs. But in reality, it's not quite like that. But I have one more thing, like this Shapley takes time. We will try it we will try it next week. All the other things that we run today, they take seconds, but to run Shapley takes about half an hour. So that we might not want to demonstrate. So I'll just show it to you. You don't have to go through. And I still have one point. Most of these things that I wanted to demonstrate or we will do together next week, mostly I got them by prompting, like telling ChatGPT, if we have this data, if we have this method, please write the Python code. So you can do the same, but you still have to understand the code. Okay, done.